for this curriculum talk. And then today his talk is about the integral quadratic forms and the lattices satisfying regularity condition.
Okay, thank you. Thank you. Appreciate the invitation to speak. I appreciate everybody taking some time out of this last beautiful summer day to be inside. So this topic of integral quadratic forms is a very old one and has its roots back in the very beginnings of ancient number theory. But what I'm going to be talking about today it's some developments that span maybe the last 20 years or so. And preparing for the talk has given me an opportunity to kind of think back to how some of these developments interact with each other. I'm going to try to give a little bit of an overview of some results and hopefully come up to date to some things that are currently being done and pose a few open problems. And rather than hold those until the end of the talk, I'll just sort of intersperse them wherever they come up in a natural way. It fits a little bit more naturally in this geometric setting. So let me set up a little bit of terminology in a little more generality than actually I'm going to need it. But the objects that I'm going to be talking about are quadratic lattices, which you can define very generally over any integral domain, just a finitely generated module over that domain that's equipped with a symmetric bilinear form that I'll denote by B and an associated quadratic form or quadratic mapping Q. And I'll say that if K and L are two such objects, I'll say that K is represented by L, or that L represents K if there's an isometric embedding of K into L. And the injective homomorphism that gives rise to that embedding, the phi in my notation here, I'll refer to that as a representation. And if phi additionally is surjective, I'll refer to it as an isometry between the two lattices K and L, and say that those are isometric. Denoted as I've indicated there, defines a nice equivalence relation on the set of quadratic lattices of, say, of a given rank. Okay, so let me link back to the classical setting. If we take a free lattice, and if I take a nice integral domain like Z, that's a PID, I know that all finitely generated modules are free, so there's always a basis. So I can always do this in at least one way. Say V1 through Vn is a Z basis for our lattice. Then any vector I can write as a Z linear combination of those basis vectors, say summation of xi vi for some xi's. And then if you just work out Q of V, just calculate out the bilinear form of V with itself using the linearity properties. You see you get that nice homogeneous degree 2 polynomial in the variables x1 through xn, the coefficients of which are given by the values of the bilinear pairing on the basis vectors. So, for example, an example that we'll see a number of times, if I take V of Vi Vj to be the Kronecker delta Ij, I'll get a lattice that I'll call In. The coefficient matrix for that lattice is just the n by n identity matrix, and the corresponding quadratic form is the sum of n squares. So a very classical example. And we know from Lagrange's theorem from 1770, we know that in fact every positive integer can be expressed as a sum of 4 squares. Well, okay, sorry. So let me go on to the next bit of notation. This is sort of a prototype example of what I'm going to call a universal form in this sense. So I'm going to need, in order to talk about definite forms, I'm going to need a notion of positivity So rather than work with an arbitrary integral domain, I kind of have to specialize at least a bit at this point. And I can do everything for rings of integers in totally real algebraic number fields, for example. I'll state most of the results just over the rational number field and the ordinary ring of integers, but most of them have been extended. Most of the results have been extended to this context of totally real number fields and their rings of integers. So then I can talk about a lattice being positive definite if Q of E always gives a totally positive element of the underlying field for all non-zero vectors in the lattice. So I'll say that a positive definite lattice is K universal for some positive integer K if it represents every positive definite integral lattice of rank K. So the statement back on the previous slide, all right, got my arrows going in the right direction. Representing integers as sums of squares corresponds to representing these rank 1 lattices by the IN lattice. So this is an example of what we call a one universal lattice in the definition on the next slide. One universal we usually just call universal, but it's nice to have this notion of generalizing to arbitrary rank sublattices. We get lots more properties.
And we don't have a sum of 3 squares of integers.
I will come to that in a minute. I will come to that in just a minute. It's an important, that's the next important example. But let me say a little bit about universality for a minute. Sum of 3 squares is not universal. And so that you can do as a quick exercise in your head. You can check and convince yourself that you can't write 7 as a sum of 3 integer squares. I can write 7 as 4 plus 1 plus 1 plus 1. But there's no way I can get it as a sum of 3 squares. So you really do need 4 here. Okay. Okay, so I'll use this notation, this use of NK, just as a convenient notation for the isometry classes of the K universal positive definite Z lattices of a given rank N. So for instance, if I look at U4-1, that would be the forms of rank of the lattices of rank 4 that are one universal, like our friend I4. So with a little abuse of notation here, I'll say that I4 is an element of that. I want to think about U4-1 as isometry classes so that I can talk about finiteness versus infiniteness. But by a slight abuse of the notation there, I'll just say that lattice is an element of that set.
So this U52 would mean what?
So U52, there's a nice other, not quite as classical as Lagrange's theorem, but there's a nice theorem of Mordel's from 1930. So you have sum of 5 squares. It says that every positive definite binary quadratic form can be expressed as a sum of 5 squares of linear expressions in the variables. That's the way the Mordell theorem would have been stated. So the fancy way to state it is to say that I5 is in the set U52.
But we don't have U51.
Okay, I'll come back to U51 here in a second as well. Yeah, I want to make a comment about that. But so there's a couple of classical examples. So let's talk about these sets for a minute. Here's U51. Okay, so what can we say about finiteness or infiniteness? So it turns out that UN1 is empty for n less than or equal to 3. For a reason that I'll explain a little bit more in a minute. So the first one that you get that's non-empty is U41, where we saw our sum of 4 squares. Now, the sum of 4 squares is in U41. So that tells you that UN1 is infinite for all n greater than or equal to 5, because you can just take any lattice into which you can embed I4. You can already represent all positive integers by I4, so therefore I can represent it by any over lattice of that. Okay, so immediately I get a whole infinite. These guys are all infinite from 4 on. And this is a very typical situation that you'll have up to a certain value of n, you'll have no k universal lattices. The first time you have any, you'll have only finitely many isometry classes of them. I don't think that reference to Ross in 1946 is probably the first place. I couldn't quite track that down. I know Ross actually has a bound on the potential discriminants of these things, and that was the first time that occurred. But anyway, there's finitely many at that level, and then for all higher dimensions, there's infinitely many. By that argument, you just embed, you can embed any one of rank n into any higher rank. So we have one interesting dimension, namely n equal to 4 in this case. There's finitely many of these things. Can we find them all? Next obvious question. Okay, so all these questions kind of have several parts. There's a finiteness part. Once you decided, okay, some set is finite, can I actually enumerate all of them? Well, that actually turns out to have quite an interesting history. There are some other examples besides the sum of 4 squares that were studied by Legendre and some of his contemporaries. There are some isolated examples of that kind. But there's a nice paper of Ramanujan in 1917 where he actually finds all of the diagonal universal quadratic forms of rank 4. So a1x1 squared plus a4x4 squared. So he finds all the 4 tuples a1 through a4 for which that's true. Turns out there's 54 of them. Actually, he had an extra one that ultimately turned out not to be universal, but otherwise his list was complete and correct. 54 of them. And this has just recently been completed using what's called the Hanke 290 theorem. I did not put a date in here because it turns out that the Hanke 290 theorem has never appeared in print, so I don't know quite how to attribute it. It's something that has been around for a number of years. It's generally accepted as correct and viable as a theorem. It existed as a conjecture for many years, but it's now accepted as a theorem. If you believe that it is, then in fact you have a complete list of all of these universal quaternary forms. It's quite a remarkable theorem, actually. There's a theorem, its predecessor is the Conway-Schneberger 15 theorem. So this was John Conway at Princeton, had a student named Will Schneberger, who finished his thesis in 1997. And he proved in his thesis, apparently, I've never seen it, but apparently he proved the following amazing theorem. So think about quadratic forms. So think about it as a polynomial, a homogeneous degree 2 polynomial, has cross coefficients, has diagonal coefficients, cross coefficients. If all the cross coefficients are even, then what Schneberger proved is that every such thing let me put it this way, such a thing is universal if and only if it represents all of the integers from 1 to 15. Period. That's all you have to check. Doesn't matter what the rank is, any rank. You don't even have to check all the numbers from 1 to 15. I think there's only 8 integers that that you have to check. Amazing. I think it's the most amazing theorem in integral quadratic, at least in the last 25 years. This, by the way, Hanky, the 290 theorem is sort of a follow-on. If you don't make this assumption about the evenness of these off-diagonal coefficients, the problem becomes much harder. And this becomes a massive computer project, basically. And this was, the paper, it was written up, paper was accepted by Invenciones to appear. John Hanke apparently withdrew the paper at some point because there was some error, not in his work, but in some paper that they were drawing on. And so he felt that it was not complete, and so he wanted to clean that up before it was finished. So it still hasn't been published, but it's out there.
So what is 290? What's this number?
So 290, it turns out that what you have to check for these with arbitrary cross terms, you have to check the representation of 29 values, 29 only, 290 of which is the biggest one that you have to check. And in fact, there exists a quaternary form that represents all the numbers up to 289, but misses 290.
And what is like roughly the year that the work was completed by Bargava and Hanke? Like roughly.
Within the past 10 years,
Okay.
the Conway-Schneberger theorem, it was never published either. Schneberger never published his work. He went to work at NSA. He's still working at NSA, I think. Bargava later published a proof of it, a very nice proof of it. And in doing so, then he sort of laid out the strategy for this 290, proof of the 290 theorem. So yeah, I'd say within the last, roughly within the last 10 years, certainly, that it's sort of gained status as a theorem. Okay, so let's look at the case for an arbitrary positive integer k. You could ask this question: is what's the smallest rank n for which this set UNK is non-empty? I said, okay, they're empty up to some point. Non-empty, the first time they're non-empty, you get finitely many, and then you get these infinite families. Okay? So what can you say about U of k? U of k turns out to be k plus 3 for small values of k. This is a proof by induction. Works for k equal 1, works for k equal to 2, works for k equal to 5.
That is true.
Must be true, right? So this new freshman would buy into that. Anyway, but in any event, I'll explain more about why that's true in a minute. But what we saw was the 4-1 case and the 5-2 case. And that continues on. You get up to 5-8. But then there's a jump. U of 6 goes up to 13. And I think the largest value for which these are explicitly known, U of 10 is 30. And then from there on, there's a lower bound that actually grows very fast from there on. U of 24 is over 6,600. So this is part of what's in Byung-Kwan Oh's dissertation at Seoul National University in 1999. There's some other stuff in there, but this is a very nice part of that dissertation. And Byung-Kwan Oh has been a major contributor in all the things that I'm going to be talking about in the rest of it. So we'll see his name popping up frequently. But this was actually in his dissertation. Seemed like I was going to say something else about that, but it'll come to me sometime. Okay. So let's go back to Kwong Ho's question. What if you only have 3 squares, okay, instead of 4? Well, the I3 lattice, everybody has now checked and convinced themselves you can't write 7 as the sum of 3 squares. But in fact, if you look at that a little bit more carefully, you can convince yourself that you can't write any number of the form 4 to the k times 8l plus 7. You can't get that as a sum of 3 squares congruent mod 2 to, well, the power of 2 that I've listed there. 2 to the 2k plus 3 will suffice. So you can convince yourself very quickly, if k is 0, you can convince yourself very quickly because the only squares mod 8 are 0, 1, and 4, again, and we just convinced ourselves we can't add 0s, 1s, and 4s and get 7. Okay, so it's easy to say when k, if k is not 0, what you do is you make the observation that, again, if the only way I can make this thing even is either to have all of them even or to have 1 even and 2 odd. The odd squares are all congruent to 1 mod 8, so then the left-hand side would be congruent to 2 mod 8, not divisible by 4. So therefore, all of x1, x2, and x3 would have to be even. Then you get a 2 divided out, and you've reduced the power of 4 that shows up. And you just work your way down. Eventually, if you could solve any congruence of this type, eventually you'd get down to one with of an integer of 7 mod 8. Okay, so the 3-square theorem, which is a little bit newer than Lagrange's theorem, is generally attributed to Legendre, says that every positive integer that's not of this excluded type, this 4 to the k times 8l plus 7, all the other positive integers can be expressed as sums of 3 squares. Okay, so there's exactly this one excluded set that you can describe by means of these congruences. So this is the notion of regularity that Dickson introduced in 1927. He said that a quadratic, he was interested in positive definite ternary forms, n equal to 3. He said that such a thing is regular if it represents all positive integers not excluded for representation by some congruence conditions. Okay? So this guy is not an example of a universal form, but it's kind of the prototype example of what we'll call regular forms. All right. So let me rephrase all of this in terms of our lattice language, our geometric language. And then we can see a little bit more the general context. So here, I could work a little bit more generally here, but I'll just restrict to the case of Q and Z to describe the setup here. So I look at Q sub P is the field of p-adic numbers, so complete Q with respect to the p-adic metric. And I take the integral closure of Z in there, and I get ZP, the p-adic integers. Okay? Can do that for each P. If I have a Z lattice, which I'll refer to as a global lattice as opposed to these localizations of it, that lattice can be extended to a ZP lattice. You just simply extend the scalars on the module. And then there's a unique way that you can extend the bilinear form on L to a bilinear form on this extended module, LP. For example, just define it on the to agree on a basis, and then extend it by linearity. This is the only way it can occur. And in fact, any representation from a lattice K to a lattice L, a global one over Z, can be extended in exactly that same way to a representation of KP and LP for every prime P. So if I have a global representation, this one, then in fact I get a whole family of these local representations, one for each prime. Okay? So, maybe an obvious question is, suppose you know that you have all of these local representations, is it possible to reverse the implication and say that will give me, in fact, a global representation? If that's the case, I'd say that we have a local to global principle for the representation of lattices. That would be wonderful, partly because the talk would be over and we could all go outside in the sunshine. Unfortunately, it's not true. But there's at least a little bit that we can say, and we can try to recover some information. What can we say? If we have all of these local representations, what can we say about the global situation? Incidentally, I should say these conditions are easy to check. If you take two local lattices, it's easy to check whether you have a representation locally that's been known since the 1960s, I guess, the early 60s. That's been completely worked out. It's worked out for QP and ZP probably in the 30s by Burton Jones. And in the 60s it was generalized to quite general setting by O'Mara. So to discuss the problem a little bit more, let me introduce what's called the genus of a lattice. So for a global lattice L, its genus consists of all the lattices which are everywhere locally isometric to it. Okay? Then there are two basic facts, neither of which are particularly easy to prove, but are true. The first one is a basic finiteness theorem, that this genus contains only a finite number of isometry classes, always. That number is called the class number of the lattice L, and I'll denote it by H of L. Okay? And the other one tells you what you, at least partly what you can say if you have this family of local representations. If I know I have local representations for all primes, then what I can say is that there exists a lattice somewhere in the genus of L that represents this lattice K. And so it sort of says, well, there's a finite failure to this local global principle in some sense, and this class number is kind of you can think of it as kind of a quantitative measure of how bad that failure is. Right? If the class number is very small, then you have a good chance of finding where this global representation is. If the class number is large, well, maybe not so good. Unfortunately, in this case, exactly, when the lattices are positive definite, these class numbers grow very quickly, either as functions of the rank or as functions of the discriminant. So they get very huge very fast. So yes, it's finite, but on the other hand, it's very difficult to get concrete, useful information. Okay, so that gives me maybe the setup to define what I mean by a K-regular lattice in analogy to the K-universal lattices. I'll say that my global lattice L of rank n is K-regular for some K less than or equal to n if it's true that for all the positive definite Z lattices of rank K, everywhere local representation guarantees global representation. So it's the lattices for which there's an honest-to-gosh local global representation principle. What can I say about these, about such lattices? So again, this generalizes in the case when K is equal to 1. These are the analogs of the regular quadratic forms of Dickson. Okay, so, but here's what we can do in general. I'll use this notation R sub n k to be, again, I'll take sets of isometry classes so that it makes sense to talk about some of these as being finite. K regular lattices of rank n. Okay? So in particular, the universal the K universal lattices of rank n are contained in there. They represent everything possible, not just those excluded by, not excluded by congruence conditions or by local conditions. Okay, so it's easy to prove this little proposition. I'm not going to go through the proof. I just put it there so you can see that it doesn't really involve very much at all. It only takes a few lines to show that R sub nk is contained in R sub nm for all m less than or equal to k. So if I have 2 regularity, I'm guaranteed 1 regularity. If I have 5 regularity, I'm guaranteed 4 regularity, 3 regularity, and so on. So it basically just involves the massaging the definitions a little bit, and using that basic fact that I mentioned a minute ago about having, if you have everywhere local representation, you have a representation within the genus, at least. So you have a little chain of containments for each positive integer n. R sub n is the smallest one, and then R sub n1 is the largest one. And I want to say a little bit about what can be said about at least finiteness for the most part, or infiniteness of these sets. So let's start at the left-hand end. These lattices in R sub n, equivalently, these are the lattices of class number 1, because in the case of a representation of an n-dimensional lattice by another n-dimensional lattice,